morning students. I am Anurag of class 12 in Kendriya Vidyalaya. I study in Jyoti classes. Today we are going to discuss about the chapter electromagnetic waves and some topics of electromagnetic waves. Today we are going to complete half of the chapter in this video. Hope you all learn. First we will in electromagnetic wave the important topics are first which will come in exam and are always frequently asked in exam. First, displacement current. Second, what is the origin of displacement current? How is the displacement current formed? Third, what is electromagnetic wave and electromagnetic wave and its formation? How it's formed? Formation of electromagnetic wave. Fourth, we will discuss about the Maxwell equations. Maxwell is a famous scientist which gave four equations based on the electric and magnetic chapters of field which we have studied before. From all this chapter, Maxwell gave four equations which are going to be worked in electromagnetic wave. If we are going to understand, first we will. These are the topics today we are going to discuss about. As the name of the chapter is electromagnetic wave, we will first learn what is electromagnetic wave. As the name suggests, electromagnetic. This word is consist of electric and magnetic. So as the name, we can all write it is the combination of electric and magnetic field. How it is made? The variation the change in electric and magnetic field vectors. It is a vector quantity which have direction as it moves in space, propagates in space. The variation in electric and magnetic field vector perpendicular to each other, The variation in electric and magnetic field vector perpendicular to each other causes them to show properties of wave. What are the properties? The properties of wave are it does not need any medium to travel in space. Them to show properties of wave. It starts showing properties of wave. And travels in space without any medium. As the definition suggests, the variation in electric and magnetic field, which shows the properties of wave as it travels in space without require of any medium. So this is the definition of electromagnetic wave. That the variation in electric magnetic field vector perpendicular to each other causes to show properties of wave. This variation shows the properties of wave which causes the formation of electromagnetic wave. The graph of electromagnetic wave can be seen like this: x-axis, y-axis. It's a vector quantity, so it will also have direction. So it is shown in graph. The upward will be electric wave like this, and from the down like this, up, 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 in straight direction, electric wave will be in straight direction, perpendicular to the direction, and magnetic wave. And from the magnetic wave will come from down below the origin. Electric wave will start from the origin and end at the origin, above the origin. Magnetic wave will start from below origin, then go above the origin, then go and end at below. This wave will be perpendicular to the electric wave, as the formation of wave occurs when electric and magnetic waves are perpendicular to each other vector. So this direction will be perpendicular. In both this is like this 2D, but in 3D you will see this is perpendicular to each other. So the direction will also be perpendicular. Magnetic waves, electric waves. This is the diagram of wave structure, magnetic wave. Electric wave. This is the diagram of electromagnetic wave. If it can come in exam in 2 marks, what show the diagram of electromagnetic wave with respect electric wave with respect to magnetic wave if it is moving in space. This is the diagram. This is perpendicular. They are perpendicular to each other in diagram. That's we have to learn. This is the definition of electromagnetic wave and electric wave graph. Now we will this is what written. Now we will learn about the important term known as displacement current. Displacement current is important term. Displacement current. Displacement current. Displacement current can also be known as modified Ampere circuital law. In the previous chapter, in the chapter moving charge and magnetism, we have studied about Ampere circuital law. In a current carrying conductor, if a circular closed loop is placed around the current carrying conductor, then the induced integral of magnetic flux will be equals to the mu naught times the current passing through the conductor. So the definition here will also be the same. If you have learned that derivation of Ampere circuital law in that chapter, it will be going to the easy. The derivation will be same. The line integral of magnetic field, magnetic field is denoted by B. The line integral of magnetic field B, this is called line integral of magnetic field B around a closed loop. Magnetic field B around closed loop. The line integral of magnetic field B. The diagram will be like this. This will be the diagram. This will be around the loop. This loop will be around the current carrying conductor. Current will move from upward direction and the loop will there. The magnetic field of B around the loop will be like this, intersecting. The magnetic field B, the line integral of magnetic field B around a closed surface is equal to mu naught times the current, passing through mu naught times the current passing through the closed loop. This is the definition. The line integral of magnetic field B around a closed loop is equal to the mu naught times of the current passing through the loop. The formula will be like this. This is the formula of Ampere circuital law. We have studied in previous chapter, but in this chapter this current will be known as ID, will be known as displacement current. Why it is called displacement current? We are going to discuss about it. Displacement current. What is displacement current? The displacement current definition is how is displacement current formed? As the name suggests, the current will displace, the position of current will displace without any medium. We are going to learn about it from a circuit diagram. From chapter 2 we have learned about capacitors and capacitance. We are going to take two parallel plate capacitors. This is the circuit. Positive, negative, battery of voltage V is attached, capacitor, two capacitor are. The current will flow from this direction to this direction, passing through the capacitance. When the charge of current comes in the capacitor, some charge is deposited in the capacitor. We know that charge deposit in the capacitor as it has capacitance value. Some charge is deposited in the capacitor. As the charge deposits the conductance of current in the wire decreases. This is the relation. As the charge of capacitance increases, the conductance of current in the wire decreases. So when the charge will get depositing here in the conductance surface, the charge in the wire will be decreasing. When the capacitance will be fully charged, when the capacitance will be fully charged, the charge, there will be not enough charge to or again, then the conductance of the wire will become zero. Meaning, we are passing charge in the capacitance, when the capacitance will become fully charged, no place for other charge, then the conductance of current in the wire, the current which is passing through the wire will become zero. When the capacitor becomes fully charged, then the current in the wire automatically becomes zero. This phenomena was we have studied in chapter 2 only. But now the current passes from positive to negative. In between the capacitor there is no medium. So how is the current passing from this to this, this to this, this to this? This phenomena, this is where the displacement of current comes. This current travels without any medium with a change in electric and magnetic flux. Electric field and magnetic flux. When the electric field and electric flux changes, this is where the displacement comes from. Displacement. The definition of displacement current can be written as displacement current displacement current is the current. Displacement current is the current which comes in play when the electric field around the capacitance and the electric flux and electric flux changes with time. Here the electric flux is changing. As before, the electric flux in the wire was of some value. Then after the conductance will become fully charged, the electric flux decreases with time. So the formula of displacement current can be given as d phi minus d phi by d by dE by dt. This is the formula of displacement current, and here it will be E naught. Displacement current in numerical we will use this formula E naught minus d phi by dt. Minus sign is there and electric flux is changing. In numericals we do not put the minus sign, as the numerical value can decrease or increase. There can be variation in value of numerical. See, this is the value of displacement current. This is the displacement current. Write it down. We have understood the source of displacement current, how it is formed, how it is used, and Ampere circuital law. Now in this Ampere circuital, we have studied Ampere circuital law in the previous chapter only. But why is this topic in this chapter? So there is a topic named modified Ampere circuital law. In this you must be wondering about, this is capacitance. There also a term known as a capacitic current. Why is not used in the formula? This is where that topic comes in the chapter where we will write it like modified ampere circuital law. The ampere circuital law which is modified. This topic comes in exam frequently. We know that formula of displacement current we have studied now only. ID equals to mu naught d phi by dt and E naught d phi we can write phi equals to EA, electric flux, electric field and area. We can write it here E naught EA by dt. Displacement current can be written like this only from one formula to another. And A is constant. We know that differentiation of constant is constant only. So here displacement current will be equals to A E naught dE by dt. Now for parallel plate capacitance, in the circuit we have to find displacement current, we have to take the value of capacitance only as it is used in the circuit, so it will have some effect on displacement current, and obviously that effect will be in capacitance E equals to V by D displacement. Now we will write it like this. Displacement current, we will put the value of E in E naught A by D dV by dt into dV by dt. We have put the value of E in this formula, so we will get like this. In displacement current new formula we will have get dV by dt. Now we know that E naught A by D equals to C. E naught A by D equals to C. Capacitance area by area of cross section into this. So we will get here displacement current equals to C into dV by dt. Now we know that amperes, and what is the formula of ampere circuital law? The closed integral of magnetic field equals to mu naught times the current. This is the ampere circuital law. We are studying the modified ampere circuital law, so hence this formula will be modified, and in the term of current there is capaciting current and displacement current. So the formula will be like this: mu naught times the displacement current plus capaciting current. Mu naught times the displacement current plus capaciting current. This will be the formula of modified ampere circuital law. In the place of C we can also write here if we value of IC if not given, we will write like this: B into DL gives mu naught times ID. Displacement current we have to find C into E naught d phi by dt. E naught d phi by dt. If we have given the flux changing with time, we will put the value of flux. Value of E naught we know it is a constant term. So this is the formula of modified ampere circuital law. These are the two formula of modified ampere circuital law. This is the derivation of modified ampere circuital law, which will come in exam, as this is the important topic of this chapter. This will only ask in the derivation. This is the only derivation in this chapter, so it will only be asked. It's obvious it will be asked. Now we are going to we are going to learn about the person who gave this term electromagnetic wave. The person who gave this term phenomena electromagnetic wave was Maxwell. The name of the person was Maxwell. The Maxwell discovered that when variation in electric and magnetic field occurs with vectors perpendicular to each other, then they start showing the properties of wave. They travel in medium with space without any medium, and hence this was named as electro and magnetic waves. Maxwell equation. Maxwell gave 4 equations, which will be come in exam. Maxwell gave 4 equations. Gauss law of electrostatics. This was named as Maxwell's first equation. Maxwell's first equation. Second, Gauss law of magnetism. Maxwell's second equation. Third, Ampere's circuital law. Induced EMF. Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. This was Ampere's third equation, and the fourth was Maxwell's circuital law. Maxwell did some change in the Ampere circuital law. Maxwell's circuital law. This was the fourth equation. These 4 equations are on the term of electric and magnetic. As we have studied this in chapter 1, chapter 4, chapter number electromagnetic induction 6, and Ampere Maxwell circuital law chapter number 4 only. This chapter. This all equation was based on the change in electric and magnetic field only. First we are going to learn about Gauss' first equation, Maxwell's first equation, which is known as Gauss law of electrostatics. The electric flux passing through any closed surface is equal to the mu naught 1 by epsilon naught 1 by E naught times the charge enclosed by the surface. The electric flux passing through to find the electric flux through any closed surface in electrostatics will be equal to 1 by mu naught times the flux. We will give the direction like this: electric flux equals to Q by E naught, 1 by 5 times the charge enclosed by the surface. This is the surface. The electric flux passing through the surface will equal to mu naught 1 by mu naught times the charge passing through the surface. This is the Maxwell's first equation. Maxwell's first equation. This was the Maxwell gave this first equation of Gauss law of electrostatics, and it also in electromagnetic wave we will study it as Maxwell's first equation. This is the formula and derivation. Now we will study about Gauss law in magnetism. Maxwell's second equation, Gauss law in magnetism. This law states that the net magnetic flux through any closed surface is equals to zero. The net magnetic flux through any closed surface is always equals to zero. This law was given by Maxwell only, but when we study in magnetism, this law was defined as Gauss law in magnetism. The net magnetic flux, the net magnetic flux passing through any closed surface is equal to zero. As we have remembered the diagram of bar magnet, we can recall the diagram of bar magnet. We remember that electric flux passes from north to south, and outside the magnet, and inside the magnet it passes from south to north. The magnetic flux outside the magnet was taken as zero. As you have remembered, if you have studied the chapter very well, you would remember the magnetic flux outside the magnet is taken as zero, and only the inside of the magnetic flux is calculated and is asked in numerical problems. This is the magnetic flux Gauss law of magnetism. Line integral of B into ds equals to 0. This is the formula. This is the diagram to remember it. The net magnetic flux outside the magnet is 0. Only the inside of the magnetic flux is calculated. I'm going to draw it. This is the second equation, Maxwell's second equation. Maxwell's second equation, Maxwell's first equation. Going to draw it. If you have studied all the previous chapter without remembering the notes plus theory, learning it, not remembering it, then you will easily understand this chapter, as it is the combination of both electric and magnetic chapters which we have studied in this chapter. Because in book 1 all the chapters are levelly equal. What chapter is the part of other chapter is only in the that. So in electric and magnetic, this is the last chapter, electromagnetic. Third equation, Maxwell's third equation was Faraday's law of magnetic induction. Faraday's law of magnetic induction. Electromagnetic induction. Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Faraday, this was the Maxwell's third equation. In electromagnetic induction chapter, we have learned this as known as Faraday's law of electromagnetic induction. This law states that the induced EMF, we have learned it. This is a closed loop. Suppose this is a closed loop carrying current. This is a not carrying anything. This is a closed loop. Simple closed loop, and this is a magnet. When the magnet is passed through this and bringing this and out, it induces EMF in the closed loop. This EMF is induced due to change in magnetic flux with time. This was known as Faraday's law of electromagnetic induction. In a closed loop, when magnet is moved inside and outside, the EMF is induced when moving of magnet inside and outside. EMF is induced in the coil. This EMF is induced due to rate of change of magnetic flux with time. This is known as Faraday's law of magnetic induction. The induced EMF produced in a circuit is equal to the induced EMF produced. The induced EMF produced in the circuit, the induced EMF which is produced by movement of magnet is numerically equal, is totally equal, number will be equal, numerically equal to the rate of change of rate of change of magnetic flux linked with the circuit. Magnetic flux linked with the circuit. Linked with the circuit. The formula will be like this: integral E into dl equals to minus d phi, rate of change of flux, changing of flux, so minus sign will be here in the derivation, d phi by dt. This is the formula of Faraday's law of electromagnetic induction, and this was given by Maxwell, and when we study electromagnetic wave we remember it as Maxwell's third equation. Maxwell's third equation. It is the third equation given by Maxwell for the understanding of electromagnetic wave. This is the third equation. Now we are going to study the fourth equation and the last equation given by Maxwell. This was known as in the Ampere circuital law. Maxwell made some modification for the understanding of electromagnetic wave. So the modified Ampere circuital law is also known as, for Maxwell equation, Ampere Maxwell circuital law. Ampere Maxwell circuital law. This law states that the formula will be this law states that the line integral, same definition of the Ampere circuital law. This law states that the line integral of magnetic field B passing through a magnetic field B passing through along a closed path will equal to the mu naught times the current passing through the closed path. The current here will be the addition of displacement current and capacitive current. The formula will be like this: line integral B into dl equals to mu naught times the current id plus mu naught d phi by dt. This will be the formula of Ampere Maxwell law, circuital law. The definition we have written before, so I am not writing the definition. This is the Maxwell's fourth equation. Maxwell's fourth equation. This is known as Maxwell's fourth equation. When we study about Maxwell's equation, these four equations we are studying. This is about Maxwell, who gave the term electromagnetic wave. Through the help of these equations we can understand electromagnetic waves. I am going to rub. Now the last topic which we are going to learn, in which all the important terms we will cover, is electromagnetic wave, cause of electromagnetic wave. This is the last topic we are learning, cause of electromagnetic wave. We have studied what is electromagnetic wave, but we have not studied what is the cause of electromagnetic wave. Cause of electromagnetic wave and its formula, laws of electromagnetic wave. We know that charge oscillates in orbit. We can write first, we will understand the definition. Charge oscillating in an orbit. Oscillating charge, oscillating we understand. This is a charge E. This is oscillating in an orbit. Oscillating charge. First we can name it oscillating charge. Oscillating charge is also known as accelerating charge. The oscillating charge moves with some speed in the orbit, so it can also be known as accelerating charge, as it moves. The speed of the charge increases in the orbit, so it accelerates. It keeps on accelerating. So this line is clear. An oscillating charge is also known as accelerating charge in an orbit. An accelerating charge, the charge oscillating in the orbit with speed will produce electric field. Charge produces electric field. It will produce electric field electric field electric field will be produced here, and we know that magnetic field is produced by electric field only. So electric field which will produce magnetic field. The electric field which is produced by the oscillating charge will now produce magnetic field due to the electric field which will produce magnetic field. And we know that from the magnetism, all the above chapter we have learned, we know that magnetic field also produces electric field due to the Faraday's law, which we have learned that magnetic field induces current in the circuit. So magnetic field also produces electric field. First the oscillating charge will produce electric field, the electric field will produce magnetic field, and again the magnetic field, and then again the magnetic field will again produce electric field. This circle goes on and on. This circle goes on and so on. And then again it will produce magnetic field, and then again magnetic field will produce electric field. This oscillating electric field and magnetic field is producing in this direction, oscillating. Then this oscillating electric and magnetic field regenerates, both gets combined. Oscillating electric and magnetic field regenerates meaning it both combined, regenerates and show properties, regenerate with each other, both combined, regenerates with each other as wave, which travels in space without any medium, as wave, which propagates through space, which travels in space without any medium, without any medium. This is the production of electromagnetic wave. This is how electromagnetic wave is produced from a single charge. The electromagnetic wave can be produced. The electromagnetic wave formula will be equal to the frequency formula only, 2 pi under root LC inductance, capacitance. This will be produced. The causes of electromagnetic wave: an oscillating charge, a charge in an orbit, oscillating, is also known as accelerating charge, as it is moving around and round. It will produce electric field. Charge will produce electric field around it, and then that electric field will produce magnetic field, and magnetic field will again produce electric field. This circle goes on, electric field, magnetic field, and then again the electric field and magnetic, at certain point the electric and magnetic field will regenerate with each other and produce a wave. The wave which travel in space without any medium, and this wave will be known as electromagnetic wave. And the formula of electromagnetic wave will be like this. This is the formula of electromagnetic wave. It is wave, so it will have frequency. So from the formula of frequency only we will find electromagnetic wave. The formation of electromagnetic wave is one more. Electromagnetic wave can also be formed. This formula is used in hospitals. Electromagnetic wave is also formed when an electron moving at high speed is stopped by a metal of high atomic number. Electromagnetic wave is also produced when an electron moving at high speed is suddenly stopped by a metal which has high atomic number. metal. Then hence the formation of electromagnetic wave, and the wave form is known as X-rays. The wave formed by this method are known as X-rays. The wave formed by these methods are known as X-rays. This is the chapter electromagnetic wave topics which we have discussed. Ampere's circuital law, displacement current, origin of displacement current, a modified Ampere's circuital law, derivation of modified Ampere's circuital law, Maxwell's equations, what happened to Maxwell to give those equations which helps in study electromagnetic wave. Maxwell's first equation, Gauss law of electrostatic. Maxwell's second equation, Gauss law of magnetism. Maxwell's third equation, Faraday's law of electromagnetic induction. Maxwell's fourth equation, Maxwell's circuital law, which can come in exam as define Ampere circuital Maxwell law, and in numerical also. And cause of electromagnetic wave, last topic. From this topic we have covered almost all the topic. Now only theory part is left, which we will discuss in other class. Thank you for your guidance and supporting. Thank you.